this is we are coming to the second talk, and second talk on this equation and all these weird phenomena when the wave function is orthogonal to itself. And the question is, how comes? How comes that the function is orthogonal to itself? So, you know what, maybe I'll start with this and then we'll continue later if you get tired, okay? So, how comes that you have such a self-orthogonality? First of all, I want to remind you that when we do this non-Hermitian quantum mechanics, we have non-Hermitian metrics that I put theta because we are using the complex scaling, but sometimes it's not because of complex scaling, just because the potential is complex. But if you restrict ourselves to these cases that I'm talking about, atomic and molecular resonances, you scale the operator or scale the basis functions, you get Hamiltonian matrix elements, and eventually you do analytic continuation, it's complex. It's not like what I told you before. Before what we did, all our trick that I said before, it was to do analytic continuation of the eigenvalues, of the energies I said before. But now I want to say, let's assume that I want to calculate the wave functions. In the method that I described you before, using the standard code, we calculate the energy as function of the scaling parameter of the basis function, and then we do analytical continuation. And then we end up only with the complex eigenvalues associated with the resonances. We don't know what are the wave functions. But let's assume that we want to do the wave function. Then there are not free lunches. You have to calculate the complex Hamiltonian matrix elements. You have to. And what I want to tell you now is something very simple in linear algebra. In linear algebra, we have these eigenvectors. Remember, these are the coefficients that I had before of the basis functions to get the resonance wave function, remember? We have this E alpha, and remember this is, it's complex in the case of resonances. And why I put here, I'm sorry, not vector. This, to tell you this, it's like variation, it's a mean value because it's not exact. This is to distinguish that we get it for a finite number of basis functions. And then we have this. And if we want to be very accurate, we need to take theta here and here, but I put it to be like this. Now, these are the right eigenvectors. And this is a column. So this is a matrix. So this is n by n. And this is it's n by 1 or 1? Yes, it's n by 1. It's a vector. Now we can write it to be like this, h theta. And instead, the right one, I can write the left one. And in order to emphasize that we don't know what it is, I put it d alpha transpose, and I put it left, because if this is n by n, this is 1 by n. So if this was a column vector, this is a row vector. בסדר? Okay? And this is equal, to call it W d alpha transpose left. Sorry, this is left. This is right. You see, this is on the left. Now we take this and we take the transpose of it. When we take the transpose of it, you change the order of the multiplicity. This is h theta times d left transpose, so it's this, equal to this equation. So, yes, excuse me, yes, toda. Yes, of course, transpose. Of course, this is very important. So when we do this, we get that the left eigenvectors of the Hamiltonian matrix are the right eigenvectors of the transpose of the matrix. Not transpose complex conjugate. Look, only the transpose of it. And then there is a theorem that says that you can, the spectrum of a matrix and its transpose is the same. So I can reordering this and such that to put here E alpha, and the notation is changed, and here I put here C alpha left. And this, I only changed the name to emphasize that these eigenvectors are the left eigenvectors, and these are the right eigenvectors, and the associated with the same eigenvalues. This is why I changed the name of it. By changing the name, you don't change the identity, of course. Yes, we want to believe it. So that so now we have two equations. One is this, and the other one is this. Transpose. Now you can see, if, forget about theta, in the case of Hermitian, H transpose is equal to H complex conjugate. So in the case of Hermitian, C alpha left is equal to C alpha right complex conjugate. Simple. So this is why we use the Dirac notation. This is why we put, and this is the bra, is the complex conjugate. Now, if the matrix is complex symmetry, H theta transpose is equal to H theta, then you should not use the left are, then in this case, C alpha left are equal to C alpha right. And therefore, what you should do is not to take the scalar product. And I put it like this because this is in the Dirac notation to take the complex conjugate, and I don't want to take the complex conjugate. And in the general case, when it's not Hermitian and not symmetric, then what you have to do is to take them to be as they are, because this is very important, that C alpha left prime, C alpha right, this is delta alpha prime alpha. This is very important. This is orthogonality property. The orthogonality property holds if and only if you use correctly the left and the right eigenvectors. And this is not something that you can choose. This is the algebra. Linear algebra tells you. So in general case, when you have a matrix, diagonalize this matrix, diagonalize the transpose, this is the Hamiltonian matrix, diagonalize it, diagonalize the transpose, and then you end up with left and right eigenvectors. And these are the only sets that will give you this orthogonality. And this delta, maybe the orthogonality is actually better to say this is equal to 0 if alpha prime is not equal to alpha. This is the orthogonality. The orthogonality condition. What I put before is to assume that you can normalize it. We'll get to it in a moment. So this is the situation which is very different from a Hermitian case, and this is the source reasons for this. This is what I want to tell you. Because I wrote it delta, but we have to be careful about this. I'll give an example. I want to give the question about this. C alpha transpose, left transpose, here forgotten to transpose, yes, transpose, times C alpha right. And then I put question mark. Before I wrote it, it's equal to 1. So I put it like this, 1 and question mark. Can I put it to be normalized to 1? The answer is that numerically, this is the question, numerically, yes, always yes, but only numerically. This is what I want to explain. I give an example when it's not like this. And so I put it, instead of example, first of all, I will give you in general. I have H11 theta, H22 theta, H12 theta, and H21 theta. I don't say even it's symmetric. This is my Hamiltonian matrix elements. This is my H theta. Okay? Matrix 2 by 2. No, I want to give example for 2 by 2.
No, larger font.
Okay? So now, what are the eigenvalues? We have two eigenvalues, which are H11 theta plus H22 theta divided by 2, plus minus half. And here we have square root H11 theta minus H22 theta plus 4 H12 theta. These are the solutions. It's here I a little bit play with transform what is written inside, not to have, you don't have what usually you know, but usually you know that it's H1, you know, it's a matrix 2 by 2. You know the roots, you can show that this is the solution. And the same thing, when you do it, you can calculate also the corresponding eigenvectors of this. And I'm telling you that when you take this, and this, and this, and this, all of them are non-zero, you may have the situation you have here degeneracy. It's non-Hermitian degeneracy, but very special. It's a non-Hermitian degeneracy which is different from what you are used to. You have degeneracy in Hermitian cases only when some parameters, this and this, are equal to 0. And this come to be equal. This has happened, for example, in conical intersection. You know, you take three atomic molecules, we have a ground state and excited state, you check the geometry, and for given geometry, this energy is equal to this energy, electronic energy, and this is equal to 0. This is, but here it's not like this. Here, none of these matrix elements is equal to 0. And you can see what it implies. It implies that H11 here, sorry, minus, well, Dan wanted me to make it larger. H11 theta minus H22 theta square plus 4 H12, oh, okay, sorry, H21. Yes, I'm sorry. H1 theta, and here H21 theta. This has to be equal to 0. And you can see that it implies that H11 theta minus H22 theta is equal to plus and minus I to square root of H12 theta, H21 theta. In the case that the matrix is symmetric, of course, it's simpler. This is what we have. So how this can happen? This can happen when the real part is equal to 2 imaginary part of this square root. And when the imaginary part of this is equal to 2 the real part of this. So there are two conditions that makes this degeneracy to happen. And if you have two parameters in your Hamiltonian, it may happen. And what are the parameters? In the case of molecules, you maybe think about the geometry of the molecules. In the case of interaction with the laser, it's the laser frequencies. I don't want to get it here, but just to show you in principle this can happen. And something happened then. When you have this degeneracy, something interesting happened to the eigenfunctions. You see that the psi plus, call it non-Hermitian degeneracy, the vector, it starts to be plus or minus I psi minus non-Hermitian degeneracy. Up to a global phase factor, they are identical. And remember that at any given point, psi, put it like this, psi left of this times psi minus right is equal to 0 because of the orthogonality. So when you get to this point, what you get? A vector that orthogonal to itself. So whenever happens this degeneracy, you get this self-orthogonality phenomena. And give you an example in numbers. It's one minus R1, I and I. This is a symmetric matrix. What are the eigenvectors of this? So 1i, 1 times 1 is 1, I times 1, so it's V0, 1i. I times 1 is 1, minus 1 times I is minus I, so it's also 0, like this. So we have one vector, so it's a matrix 2 by 2. The number of the linear independence eigenvectors is only 1. This one. And you take, it's symmetric. So if it's symmetric, you need to take this product. And this is equal to 0. This is a term that I put years ago, self-orthogonality. Self-orthogonal states. So, and it's associated in linear algebra to Jordan blocks. It's matrices that are not diagonalizable, because you can transform it to be real symmetric matrix when here it will be 0 and here will not be 0. You can, this is known as Jordan blocks. And in the book, there are exercises to show it. So what I want to say that from terms of algebra, the price that we pay, this is what looks like a price, but in the moment I'll tell you why it's not a price, that this 1 is not really 1. It can be, sometimes it's 0. This is in the case of non-Hermitian degeneracy, which is a branch point in the spectrum, branch point because two eigenvalues coalesce. This is another name to this, and this is what people call it today exceptional point. So all these three names related to the same phenomena, that the two eigenvalues coalesce when the corresponding eigenvectors become linearly dependent. Linearly dependent because it depends only, one is equal to only a phase factor. And then it's equal to 0. But in the numerical calculation, it's never 0. Let's assume the numerical calculation is 10 to the minus 20. Okay? You cannot get such an accurate because of round-off errors. So what you do, you divide this by 10 to the minus 10. You divide this by 10 to the minus 10, and then it's come to be 1. So when you do the numerics, and you normalize it to be unity in this language, the C normalization, or non-Hermitian situation that you, as I said it here, you always can make it to be like this, always in the numerics. The numerics, yes. But how you can see, then when you do it, you'll see that you have two eigenvectors that looks very close to one another, and each one of the elements in the vectors is huge. If it was to be 1, you need to divide it, the computer will divide it by 10 to the minus 10. So each one of the matrix elements will be extremely large. So when you diagonalize non-Hermitian matrix, look at the eigenvectors, normalize them to be unity following the C normalization, not Dirac. And then if you take the Dirac product, you get infinity, or not numerical infinity, extremely large values. As it's larger, it implies that you are closer to this non-Hermitian degeneracy. So this can happen, and this is the reason that I put it here. And then, okay, the question is if it's related to something that can happen in physics. Is it artifact of the mathematics? I have to tell you that many years I thought that this is artifact of the mathematics, or this is something really real. And here, and with this I will finish, there are two examples without getting into detail to tell you, look, there is something in it. Well, first of all, I want to describe two time-independent adiabatic symmetrical switches, and the second time-dependent asymmetric switch. And actually, recently, experiment was done based on our theory that show in experiment how this can happen. So non-Hermitian degeneracy, what I told you, you have a branch point, incomplete spectrum. Why it's incomplete? Because you have a matrix 2 by 2, and you have only one linearly independent vector. It can be happen, of course, if it's large matrices, of course. We will never solve matrices 2 by 2, but it's happened always. Can happen to us always. And here is a little bit of the theory. It's a lot in chapter 9 of the book. The eigenvalues, at this, so let's assume that you have a parameter lambda at which this branch point happened. And to make it simple, I assume that this lambda is complex, but it can be, instead of having one complex parameter, you can have two real parameters. You can understand it. So around the branch point, this has happened, and you see Why it's coming to be a branch point? Because when lambda is equal to the lambda branch point, then this is disappear and you have only this. And it's not analytical in this point. This is why it says it's a branch point. And if you take the derivative with respect to lambda, at this, when lambda is equal to lambda branch point, you get infinity. So this is one of the indications. It implies that if you make a plot of the energies as function of lambda, you get a point when they get together, and it's a cusp condition. The derivative is not well defined in this point. So it's like a cusp, like in the Gothic arches, I think you can see such a cusp like this. And now let's assume that we make a loop around this. So I defined in the parameter space, I take lambda minus lambda branch point to be R, EI phi. Phi is the angle. So the energy is equal, because of this expression, to be like this. And then you can see that when you take a loop, you end up with the plus solution is turned to be the minus solution, and the minus solution comes to be the plus solution. So when you make such a loop, you switch from one eigenvalue to another eigenvalue. Actually, also from the eigenvectors, from one eigenvector to another eigenvector. So this is interesting because I can say here that here we have adiabatic switch. Adiabatic switch. You have a parameter lambda in your Hamiltonian, and you change it adiabatically, and then 1 is coming to be 2, and 2 is coming to be 1. When you do such a circle. So the simulation to molecular hydrogen ion in strong laser field switch from one vibrational state to another. This is the example. It's only the computer, of course, because you'll see it in a moment. I'll tell you why. And here, this was done with Roland Lefebvre. Roland Lefebvre visited me for many, many years, and I visited him for many, many years. And one of his visits, you see 2009, he showed me what calculation he's doing with Osman Atabek from Paris. And when he studied the photoionization of H2+, and when he showed me what they are doing, I told him, you know, if you turn on the laser parameters, which are the frequency, the wavelengths of the light, and the intensity to be very specific value, you will see the phenomena that I call self-orthogonality. How he could find it? When he diagonalized the Hamiltonian, when he has the two electronic surfaces and coupled by the laser, I can show you how it's done. It's very simple. It's actually using a Floquet theory. And he assumed that the laser is not so strong. Here you see this is the intensity of the laser here. This is the parameter here. And for this is the wavelength of the laser. He got a branch point. When the 9th and the 10th vibrational states coalesce, the Hamiltonian is non-emission because the excited states of H2+ is repulsive, and the ground state is bound. So in the moment you couple the repulsive to the ground potentials, you get dissociation. So we complex scale the Hamiltonian to describe the dissociation decay rates, and you have the 9 vibrational state dissociate because of the interaction with the laser, and the 10 vibrational states dissociate because of interaction with the laser with the upper repulsive potential, electronic potential. And when you match the parameters, you get this coalescence. And Roland saw it, as I said. He normalized all the eigenvectors to be 1, then look at the scalar product. Then he saw the two of them get very large values because he wanted to make sure that it's correct. I have to say that he did the calculation so accurate until he get that each component of these eigenvectors was really 10 to the plus 20 or 15, I remember. So huge. And then he come and say, Nimrod, from now I believe you. And so this is, I'm telling the story. And actually, he did beautiful piece of work because then what he did, he changed adiabatically. This is what I expected, that if you go adiabatically with the parameters, you will get the switch that I told you before. How to do this adiabatic switch? You do first the calculation. For example, here is zero field, so nothing. Then you take the field a little bit and the wavelength to be like this, and then you get two eigenvalues. And you follow the one that is closest to the eigenvalue that you had before. So if you start with the 9 vibrational level, let's assume, you follow the one that is closer to the 9 one. And then you turn on the intensity more, and you have again two solutions. Which solution do you take? The one that is closer, has largest overlap with the wave function that you had before. So you do it step by step. In each step, you choose the solution that has a larger overlap with the solution that you get before. So this is how you assure that you associate all the solution with the 9 vibrational level. So let's assume that you start here with the 9. So you follow, so when you look at the energies, you see that they are doing like this. And you get to the 10. And if you start with the 10, it's coming to the 9. So you get a switch. Now, if you do this change in the parameters, when you leave the exceptional point, the branch point, out of the loop, then I expect to have what you usually get in a adiabatic calculation. You will get, of course, losses. Of course, H2 plus will dissociate. But when you do this, look at the red one. The 9 return to the 9. The 10 return to the 10. So in order to have this phenomena, you have to know where is the branch point. So let me tell you, let's assume that you don't care about non-Hermitian quantum mechanics, and you don't calculate the photodissociation using non-Hermitian quantum mechanics. You do it any other way. And you start with a 9 vibrational level, and you apply these laser parameters, and you check what is the decay rate of this molecule, dissociation decay rate, and the energy of it. And then you see that it's as the laser parameters like this. And then you change the loop to be something else, and you don't know about this. And then you get a switch. If you do standard Hermitian calculations, and you get this phenomena, and you see it's very sensitive. If you are included here, you'll get it. You do it here, you don't get it. So I think it's some numerical instabilities. If you don't have explanation, and you see that the phenomena disappear, as you change very little the parameters, and you don't know the explanation, I'm not saying that you don't publish it, maybe in the journal of irreproducible results, because you change a little bit the parameters, it disappear. But when you know the branch point, you know it's physics. Now the question is, can you make such experiment? Well, in molecules, no, but in microwaves, you can do something in this spirit, and this type of experiment has been done. But when you do such experiment, you see the following only on the computer. Because when you do the experiment, always you get the two solutions, and you need to follow the one that is very close to the one that you got before. So all these phenomena is in the computer and not somehow in the measurable quantity directly. So what we thought is to change, to go along this path here in time. So use chirp laser pulses. So take a pulse that as function of time, make this loop, or this loop, or this loop, and then see what's happened. And then there is a big surprise that when you do this, so call it chirped laser pulses. Chirped implies that the frequency is changed in time, and also the intensity is change of time. So you turn on the laser, and you turn it off, and during this time, the frequency of the laser is increased or reduced. This is called chirp. This is how you can design such a loop. Actually, there is no need to return to the same point. You can do it. It doesn't matter where you return, because you can close the loop doing like this. Return here, and then it's close the loop. And then what you see, one go to 2, but 2 remains 2. It's asymmetric. Which one is 1 and which is 2, it depends on the case. So you do this asymmetric, and why it's asymmetric? Because if you do it, you turn on the laser in the backward, instead of going like this, now you'll go in the other direction, you'll get the opposite. You'll get that 1 will remain 1 and 2 will remain to 1. So it's asymmetric. So in one direction you get this. Let's assume that it's when the laser pulses is changed in this direction, in the loop of the parameter space. And if you take it to the other direction, you get that 1 is go to 1 and to 2, sorry. No, to 1, I did it correctly. And 2 is going to 1. So this is asymmetric switch. And here I finish. This is what I told you before. Adiabatic symmetric switch, this is what we see. In every experiment, the laser parameters are held fixed. Now, time dependent. This is what I told you before. Achim Richter have shown it in the experiment with the microwaves experiment. Achim Richter for Germany. He was the master of this kind of experiments, I have to say. And then we come to time-dependent asymmetric switch. The theory, it started by Ram Uzdin, that was a PhD student with me, together with Alexei Mariebev. He's a mathematical physicist from Brazil. Actually, originally, he was a professor in Moscow University. And this is the first time that we introduced this idea. So this is what I said, clockwise and anti-clockwise. And this is the explanation why it's not working. And I think this will be close to the end. But I think it's important, so I need to tell you. We write here the Hamiltonian when we take the interaction with the laser, and I skip on how we get this to this situation. And I want to say that what we do, this is the off-diagonal matrix elements. When you do it in time, you see this phi depends on time. So when you do the calculation, you get the energies, the complex one, and you get the eigenvectors. In the adiabatic solution, it implies that the phase factor is the integral of this. And now, in the matrix elements, the coupling between them, you think about this phi is like coupling because of time. You take this solution, couple to this solution, and it's possible to show that this is the matrix elements. And here you have this phase factor. Now, if the phase factor was Hermitian, the off-diagonal matrix elements, this one, are vanished if it was Hermitian. Because if this is real and this is real, so this is a number. And if you take here t to be infinity, namely you go doing it t is the time that it takes to do this loop. If it's going to infinity, this is going to 0 because of this factor. And this is actually the base to the assumption of Michael Berry when he proved the Berry phases. He baked the proof on the adiabatic approximation. And he said, I don't need to show it for the exact one, because in the adiabatic, in the Hermitian case, as you go more and more slowly in time, the off-diagonal matrix elements which rise because of the going beyond the adiabatic approximation get to 0 because of if you go slowly enough. But in our case, there is something different. These are complex. So if they are complex, there are two options. That the imaginary of the difference of these is negative. Let's take this first case. So it's minus, the imaginary part times minus is plus, I times I is minus. So this go to 0 not because of this t is going to infinity, because exponentially goes to 0 because t is increasing. So the adiabatic approximation that we did before in such a case holds even better than usual. But if this is equal this situation and this go to 0, this is going to infinity because there is inverse sign here. So if this go to 0, this is going to infinity. If this go to infinity, this go to 0. You get non-symmetric matrix. And this is the source of the non-symmetric switch. Now, how comes that you don't have here anything in the adiabatic approximation, and how to show that this is the Hamiltonian matrix elements? This is out of the scope of this brief introduction, but I just want to give you the feeling why it's happened. It's happened because in the adiabatic approximation, the phase factors are this. And if the couplings, you have the difference between them, then you have to get this asymmetric switch. And indeed, there is a simulation with Ido and Alexei. It was for the same H2 plus that I showed you before, that we did with Roland Lefebvre. With this is, and now we took one loop like this, exactly like before. And you can see the clockwise direction is, excuse me, you start with the 10, and the probability to get to 10 is getting to 0 in the end of the pulse. And you start with the 10 and 0 population of this one, which is the 9, you see in the end of the loop you are here. So you start at the beginning, 10 is 1 and 9 is 0. You end up with 9, the probability is 1, and this is 0. And you get, of course, losses, but we normalize it so you don't see the losses. But of course, not all the molecules survive. The molecules that survive during this laser pulse, they don't dissociate. The H2 plus will be, in the beginning, if they were at 10, they will be now at 9. And counterclockwise, if you start with the 10, you see you remain with the 10. And if you start with the 9, you go to 0. So you get just the opposite. It's, of course, look at this, how crazy it is. You start here with the 10. During the pulse, this gets almost to 0 population probability, and then return to 1. And again, it's normalized to 1 only because we didn't, we normalize it such that you don't see the losses because of the photodissociation. And here to say that instead of doing this loop, you can do such a loop. You don't really have to start a return. You can start like this. And then, and this, the reason here that this is a positive chirp. If you go this direction, is a positive chirp. If you go this direction, is a negative chirp. This is something that experimentally you can do. And the loop is closed here at 0. You can assume that the loop is like this, like this, like this, and like this. And the positive chirp, a negative chirp, this is what he did the calculation. And experiments based on this, our theory, was published recently in Nature. You can look at it. There are many people others than us, but the idea came when I represented in a conference that was in En-Gedi, and the people who are running all this simulation was Alexei and Stefan and their students, and it shows that it works. Okay, so here I show you for optics, for atomic and molecular physics, they are then more fields. The answer is yes. They are yes to surface science, to laser physics, molecular, nuclear, physics for energy particles. To all these subjects we have done work to show how these exceptional points and all this non-Hermitian quantum mechanics helps. I'm not sure that exceptional points we did to all subjects, but non-Hermitian definitely to all of them. This is a pre-dissociation phenomena. And well, this is part of my talk, so let's acknowledge to all the people with them I did this work. Okay. So next next week I'm not here, and then when we return on Tuesday, Ofer, if you will remember, he will come, and maybe we'll give this. If not, Anael will talk about it. Okay, I'll call him. No, it's not.